Welcome to The Explainer. Today, we're going to dig into something pretty fundamental. How do we actually measure our planet's greenhouse gas emissions? We're talking about the entire framework, from the tiniest microbial processes in the soil all the way up to a global view from the atmosphere.
So all our climate goals, all those big targets you hear about, they're all built on data. But that brings up a huge question. How do we actually trust the numbers? The answer isn't just one simple measurement. It's a really rigorous, multi-layered system designed to make sure that when we talk about emissions, the data is solid, transparent, and comparable across the board.
Think about it. If you want to compare emissions from, say, Brazil and Germany, you need to make sure everyone's playing by the same rules, right? And that's where the IPCC, the Intergovernmental Panel on Climate Change, steps in.
What the IPCC does is provide this incredibly detailed set of guidelines so countries can build what's called a national GHG inventory. The whole point is to make sure these inventories are comparable, complete, and consistent over time. And that consistency part, it's absolutely crucial. It means we can tell if emissions are actually changing, or if someone just changed how they do the math.
To make this work for everyone, the IPCC came up with a tiered system. Tier 1 is pretty basic. It uses global default numbers. But as you move up to Tiers 2 and 3, things get way more specific. You start using country-specific data, complex models, even direct measurements. It's all about getting more accurate, localized estimates. So, okay, this is the how-to guide, but where does the actual data come from? Let's start from the ground up with what's called the bottom-up approach.
All right, so the first big strategy we're going to look at is the bottom-up approach. And it's pretty much what it sounds like. You meticulously identify every single source of emissions, whether it's a factory, a city, or a whole country, and you add them all up to get a grand total.
You can really think of it like making a super detailed budget. But instead of tracking money, you're tracking every puff of smoke from a factory, every bit of exhaust from a car, and even emissions coming off of farmland.
Okay, so for the big polluters, think power plants, giant industrial facilities, a key tool is something called a Continuous Emissions Monitoring System, or CEMS. These are instruments stuck right onto smokestacks, and they give you a real-time feed of what's coming out. And to make sure that data is legit, you have these tough certification schemes, like MC-ERTS, that require super strict calibration and regular checks. No fudging the numbers here.
But smokestacks are just one piece of the puzzle, right? What about all those emissions that don't come from a single pipe? I'm talking about huge sources like agriculture and land use, which produce a ton of methane and nitrous oxide. Measuring that stuff, well, that requires a whole different set of tools.
And here are two of the main ways scientists do it out in the field. On one side, you've got the Eddy Covariance Tower. It's packed with high-tech sensors that measure how gases like CO2 and methane are moving between, say, a whole forest and the atmosphere. And on the other side, you see a static chamber. It's a much simpler idea. You basically put a box on the ground to trap the gases coming out of a small patch of soil so you can measure them really precisely.
And this really gets at a super important trade-off. Those chambers, they're perfect for controlled experiments. You can see exactly how different fertilizers, for example, affect emissions side by side. The tower, though, that's giving you the big picture. It's capturing the combined breadth of the entire landscape, continuously, showing you what's happening in the real world.
Okay, so we've been looking at things from the ground up. Now let's completely flip our perspective and look from the top down. This gives us another powerful and totally independent way to see the big picture.
So instead of adding up all the little sources on the ground, the top-down approach measures the greenhouse gases that are already in the atmosphere. Then, and this is the really clever part, scientists use these complex models of how air moves to work backward and figure out where those emissions must have come from. And they do this using everything from satellites and planes to drones.
And this is where amazing technology like NASA's OCO3 comes in. It's mounted on the International Space Station, giving us this incredible bird's-eye view. By mapping CO2 all over the globe, it gives us critical data, especially for places where getting good on-the-ground info is next to impossible.
And this quote from NASA just nails it. They can use the data from OCO3 to calculate emission estimates for dozens of cities all around the world. I mean, think about that. From space, we can basically take the pulse of an entire city's CO2 output. It's a fantastic way to double-check what's being reported from the ground.
Okay, so let's recap. We've got two totally different ways of looking at this. One is building up from all the little sources on the ground. The other is looking down from the sky. So the obvious question is, which one is better? But you know what? In climate science, that's really the wrong question to ask. It's not about picking a winner.
Because the real power, the real scientific magic, happens when you bring them together. It's all about using them as a system of checks and balances. When you compare the two, you can start to really nail down the numbers and get a much clearer picture of what's going on.
Yeah, this table really shows you how well they complement each other. The bottom-up method is fantastic for policy because it tells you exactly which source is the problem, which valve you need to turn. But the top-down measurement, it can spot things the inventory would totally miss, like a massive hidden leak from a pipeline you didn't even realize was there. One method tells you what you know is there, the other tells you what's actually there.
So, putting these two approaches side by side, it's just a critical quality control step. It's how we find those gaps between what's reported and what's really happening. It helps us hunt down those hidden fugitive emissions, and it gives us confidence that our climate policies are having a real impact.
So why do we go through all this trouble? Why does this complicated system of measuring and double-checking even matter? Well, because pretty much everything we're doing to tackle climate change, from the big international agreements like the Paris Accord all the way down to a company's sustainability goals, it all hinges on getting the accounting right.
And it all comes down to three core principles. First, transparency. Your methods and your data have to be out in the open for anyone to check. Second, precision. Your measurements have to be sharp enough to actually see if things are changing. And third, consistency. You have to use the same methods over time so you're not comparing apples to oranges. These three things together, they're the bedrock of trust in climate science.
And that leaves us with a really fascinating question to think about. As our technology for measuring emissions, both from space and on the ground, gets better and better, how is that going to change how we actually tackle climate change? That's our explainer for today. Thank you for watching.